My name is Skylar McCaw, and welcome to my Lab 1 video for Physics 2211, which focuses on constant velocity motion. The experiment involved recording an object moving at a constant velocity with no directional changes and using Tracker to analyze and extract the data from it. Using information gleaned from Tracker, I then created a model of the experiment using GlowScript. Lastly, I entered the position time data from both Tracker and GlowScript into a spreadsheet and made a graph comparing them. The goal was to see Newton's second law in the real world as well as in the created model. The form of Newton's second law I used to create the model was V final equals V initial plus net force divided by mass times change in time. Because the goal of the experiment was to have a constant velocity, this means that V final must be equal to V initial. This also means that F net over m times delta t must equal 0. Since the time interval is not 0 and mass is not 0, F net must be equal to 0. F net must also equal 0 due to Newton's first law. An object moving at a constant speed will remain moving at the constant speed and in the same direction unless an outside force acts upon it. Because the object is moving at a constant velocity in the experiment, there must be no net force acting upon it, so net force must equal 0. Because net force equals 0, the following equation can be used, with V average being calculated using V initial plus V final divided by 2. The previous equations alongside this one can be used to model the future motion of the object in the modeling portion of this lab. Here's the video of the experiment loaded into Tracker. I rolled a ball across a flat surface and recorded it with as little angle as possible so as to get the best results. The origin is placed at the center of the ball in the first frame, and the ball rolls horizontally in the negative x direction. The analyzed portion of the video is 0.968 seconds long, and I marked the positions of the ball 29 times based off the 29.9 frame rate. Based off of the analyzation Tracker, I was able to get this information. The initial position is 0 meters on both the x and y axis. The initial time is 0 seconds. The mass of the object is 0.024 kilograms, which I found by weighing it, not from Tracker. I also found delta t to be 0.033 seconds based off the frame rate. I also calculated the initial velocity based off of the first two data points and found it to be negative 0.947 meters per second. I took all this information and plugged it into the program I had created in GlowScript, shown here, and produced this model, with graphs of position versus time and velocity versus time and corresponding data points. I then took this data alongside the data from Tracker and put it into a spreadsheet. This is the graph I produced when using a spreadsheet to compare the data. The blue line is the data from the experiment itself, and the red is from the model. As you can see, the model predicts further motion than the experiment itself, and at the end of the time interval, the positions are quite far apart. This is most likely due to the fact that while the ball was meant to roll at a constant velocity, it probably did not, so the final velocity would be less than the original, causing a smaller change in position as a result. To test this theory, I found a different average velocity, using the first and last data point from the experiment instead, which would be a better reflection of the overall velocity rather than just the first 2 points. When doing this and using the new velocity to create a model, the experiment and the model lines were much closer together. What if the x-axis was flipped? In my video, the ball moved in the negative x direction, so the final graph should align with negative slope. If I had flipped the x-axis, then the object would be moving in the positive x direction, and the graph would look like this instead, with a positive slope. It is easy to say that F net equals 0 in the model because I was able to assign that value in the code. But for the experiment, it is much more complicated. I would need to be able to identify every force acting on the ball over the course of the video and to what extent it acted. I would also have to show how they canceled each other out continuously to get F net equals 0. In reality, it is most likely that F net does not equal 0 in my experiment video, as shown in the first graph I created where the final positions were so different. So it would be impossible to prove that it does. Thank you.